Welcome back to the deep dive. We're jumping straight into one of your requested source materials for IGCSE Physical Education Anatomy and Physiology.
That's right.
And today, we're starting with the very structure that holds you up, the skeleton.
Exactly. And for everyone in the Revised Direct family, this is our fast track. We are not just listing things. We're going to unpack the essential functions, nail the anatomy, and connect it all to actual movement.
All to save you time.
Maximum insight, minimum time.
Okay, let's break this down then. We'll start with the core roles of the skeleton and take a full tour of the major bones and wrap up with how it all works in motion. The idea of bones as levers.
Sounds good.
So let's start at the very beginning. What are the four essential functions?
Well, the first two are the ones you can kind of see. We start with shape and support.
Okay.
It's the body's fundamental framework. I mean, without it, you'd basically be a puddle on the floor. It gives you your shape and supports all your muscles and organs.
And that rigid structure leads directly to the next function, which is life-saving, really, protection.
The skeleton is like your body's natural armor. For your exam, you absolutely need two key examples.
Which are?
First, the cranium. It's that solid helmet protecting your brain.
Right.
And second, the ribs. They form a cage around your heart and your lungs.
The two most critical examples. Now, for us PE students, the third one is where it gets really practical. Muscle attachment for movement.
This is everything. Bones give muscles a firm anchor point. So when a muscle contracts and pulls, it needs something solid to pull against.
That's what creates the movement.
That's what creates all athletic action. We'll dive deep into the mechanics of that in part 3, but for now, just no skeleton, no movement.
And the final function. This one is a bit of a surprise, I think. It's a biological process happening deep inside the bone.
Yeah, red blood cell production.
So why does something that sounds like it's from a biology class matter so much for sport?
Great question. It happens in the marrow, which is found inside the larger bones. Now, red blood cells are your oxygen taxis. They pick up oxygen from your lungs and deliver it to your working muscles.
So it's all about performance. If you're running a long race or in the last quarter of a match.
Precisely. You need that continuous oxygen supply to fight off fatigue. So a healthy skeleton is directly fueling your endurance. It's not just about being strong, it's about powering your entire system.
That's a fantastic link. Now, before we get to naming all the bones, we should probably talk about what they're made of, or rather, the different types. They're not all the same shape, are they?
No, not at all. And the shape tells you the job. There are 4 types you need to know: long, short, flat, and irregular.
Let's start with the obvious one for PE, long bones.
Yep. Think of the femur in your thigh or the humerus in your arm. They're longer than they are wide, and their whole purpose is leverage for movement. And, importantly, they contain that marrow we just talked about.
Then we have short bones, cube-shaped, you said.
Pretty much, like the carpals in your wrist or the tarsals on your ankle. They're all about stability, shock absorption, and allowing for small, fine movements.
Okay, next up, flat bones. The name is a bit of a giveaway.
It is. Things like your cranium, your scapula, the shoulder blade, and your ribs. They're thin, often curved, and they're either for protection or for providing a huge surface area for big muscles to attach to.
And the last one is the catch-all category, right? Irregular bone.
Exactly. If it doesn't fit the other 3, it's irregular. The classic example is the vertebrae in your spine. Their shape is super complex because they have to do multiple jobs at once: protection, flexibility, and muscle attachment.
That gives us the context we need. So now we know what the skeleton does and the types of bones it uses. Let's get to the part everyone needs for the exam, the anatomical tour.
Let's do it. We'll go top down, nice and systematic.
Okay, guide us through the upper body. What are the key names we need to know?
Starting at the very top, you have the cranium. Then for the shoulder, you've got the clavicle, that's your collarbone, and the big flat scapula behind it, your shoulder blade.
Got it.
Then the single bone of the upper arm is the humerus.
And below the humerus. Okay, this is where it gets tricky for a lot of students. The 2 bones in the forearm, the radius and the ulna. How do we keep them straight?
There's a simple trick. The ulna makes the bony point of your elbow. The radius is always on the thumb side of your forearm.
Oh.
So think of it like this. When you turn your hand over, the radius rotates. R for radius, R for rotation. Or just remember, radius is by the thumb.
Simple, clear, effective. Perfect.
Then, to finish the arm, you have the wrist and hand bones. It's carpals for the wrist, metacarpals for the hand, and phalanges for the fingers.
Right. And you mentioned the vertebrae earlier. We can't really talk about the body's core without touching on the spine, the vertebral column.
Absolutely not. It's central to everything. It protects the spinal cord, but it also has these cartilage discs between each vertebra that act as shock absorbers.
So every time you run or jump.
Those discs are compressing and protecting your joints from impact. It's an incredible piece of engineering.
Okay, let's shift to the lower body. This is where we get into the heavy-duty, weight-bearing bones.
Definitely. We start with the pelvis, or the hip bone. It's this massive, stable anchor point for your core and leg muscles.
And connecting into the pelvis is the big one.
The femur, the thigh bone. And a key fact you must remember, it is the longest and strongest bone in the body.
The longest and strongest, got it.
Then, covering the knee joint, you have the patella, which is just the kneecap.
Okay, and just like the forearm, we hit another pair of bones below the knee, the tibia and the fibula. What's the direct tip here?
It's all about function.
Okay.
The tibia is the big, thick one on the inside of your leg, your shin bone. It bears almost all your weight.
Right.
The fibula is the thinner one on the outside. Its main job is muscle attachment and stabilizing the ankle. So I always say T for thick tibia and F for fine fibula.
That makes it easy. Tibia takes the load.
Exactly. And to finish our tour, we have the ankle and foot. The key bone in the ankle joint is the talus. Then you have the tarsals in the ankle, the metatarsals in the main part of the foot, and finally the phalanges again, but this time they're your toes.
So we have the full list of bones. But bones on their own don't move. We need to talk about the connections, the joints.
A critical point. Movement only happens at a joint, and there are three main types based on how much they move.
Run us through them quickly.
First, you have fixed joints. Think of the plates of the cranium. They don't move at all. Their job is just protection.
Okay.
Second, slightly movable joints. The vertebrae in your spine are the perfect example. They allow for a little bit of movement, like bending and twisting.
And the third type is the one that matters most for sport.
The freely movable or synovial joints. Your knees, hips, shoulders. These are what allow for all those big athletic movements.
And they have a really specific structure, don't they?
They do. They're held together by ligaments, which connect bone to bone. The bone ends are covered in smooth cartilage to reduce friction.
And there's fluid in there, too.
Yes, synovial fluid. It's like oil for the joint, keeping everything moving smoothly. Ligaments, cartilage, fluid, that's the magic combination for athletic movement.
Which brings us full circle. Let's get to the practical application. We've said bones act as levers. What does that actually mean when you're on the court or the pitch?
This is where the physics comes in, and it's highly testable. A lever system always has three parts. A fulcrum, which is the joint.
The pivot point.
Exactly. A load, which is the weight you're trying to move, and an effort, which is the force from the muscle.
And the order of those three things defines the type of lever.
Precisely. Let's start with the first-class lever. Here, the fulcrum is in the middle. The setup is load fulcrum effort.
Like a seesaw.
A perfect analogy. In the body, think about nodding your head back. The load is your head's weight, the fulcrum is your neck joint, and the effort comes from your neck muscles.
Okay, what about a second-class lever?
Here, the load is in the middle. So fulcrum load effort. These levers are built for power. The best example is a calf raise. The ball of your foot is the fulcrum, your entire body weight is the load, and your calf muscle provides the effort by pulling up on your heel. It's designed to move a heavy load.
And the final one, the third-class lever. You said this is the most common.
By far, especially in our limbs.
Okay.
Here, the effort is in the middle. Load, effort, fulcrum. Now, these are not for power. They're built for speed and range of motion.
So an example would be?
A bicep curl. The elbow is the fulcrum. The bicep muscle attaches close to the elbow. That's the effort. And the load is the weight in your hand. The setup lets you move your hand really quickly over a large distance. Same for kicking a ball.
This is key. So every time you sprint, throw, or jump, your body is using these lever systems, with your skeleton providing the rigid bars and your joints acting as the pivot points.
That's the synthesis. We've covered the four functions: support, protection, red blood cell production, and movement. We've identified the bone types, toured the anatomy, and unlocked the mechanics of the three classes of levers.
You now have that core foundation for this entire section of your IGCSE.
And as a final thought for you to take away, we said the femur works as a third-class lever when you're sprinting, which is all about speed over power.
Right.
So think about this. How does the precise location where a muscle's tendon attaches to a huge bone like the femur affect the trade-off between speed and power? How does anatomy fine-tune that lever for maximum sprinting velocity?
Something to think about, that mechanical advantage. This deep dive
Yeah.
should be your go-to starting point. Whether you're looking at the skeleton infographic or listening on the move, you have the structure, the facts, and the key insights.
Use this knowledge, apply it, and you will excel. End of deep dive.